Okay, so next we will consider the isothermal core equilibrium. Okay, now you see in hydrostatic equilibrium, the pressure supplied by the isothermal core as calculated from the core outward should equal the pressure caused by the weight of the envelope above it as calculated from the surface inward. Now what we are going to do is so basically by imposing this condition, so let me again restate this. So in hydrostatic equilibrium, pressure supplied by isothermal core as calculated from the core outward, it should match basically the pressure caused by weight of the envelope above it as calculated from the surface inward. Okay, so now by imposing this condition we can obtain a constraint on the mass of the isothermal core. So MIC, mass of the isothermal core, as a fraction of the total mass. So let us define the mass fraction Q as MIC divided by the total mass of the star. Now let me show you the basic configuration where we will impose this condition that we have just talked about. So basically P IC is equal to P envelope. Okay, so this is the diagram that I wanted to say. So this is our isothermal core and this is the total star. So the scenario is like this: the total star, and the inside we have the isothermal core, and this is the total star. Okay, and the star has mass m and the isothermal core has mass MIC, and this is the same old picture over here, and this is the thing that we were talking about, the condition of equilibrium between the two pressures. Okay, so what next? Let us start by calculating this envelope pressure. Okay, now how do we estimate this? We can start our estimation here. You see, let us start this calculation of envelope using the equation of hydrostatic equilibrium. So this is just P0 to P envelope dP, and this gives me M to MIC, the integration will be over there, Gm dm divided by 4 pi r to the power 4. What is the reason for this limit? You see, the integration has to be done for the total mass up to this mass. The mass is MIC and this is the total mass over here. Okay, now the precise value of this integral depends upon the mass distribution of the envelope, of course. Anyway, without going into the mass, so this depends on the mass, depends on mass distribution of envelope. Now we are not going to do the exact calculation. However, what we are going to do is we are going to use some tricks. Let us use, say, dimensional considerations. Dimensional considerations. Then, you see, using the dimensional considerations, we can approximate this integral like using this. You see, so this is basically minus g by 8 pi r average to the power 4. Okay, and here mic whole square minus m square. This is it. Now, this is dimensional consideration. Next, what we are going to do is, we are just going, this is again quite funny. What I am going to do is, I'll assume that this weighted value of r from the integral here, this r average is the weighted value, weighted average of r to the power 4 from the integral, okay, over here. Now, so what I am going to do is this thing. I am going to assume that r average value of r to the power 4 is approximately half of the maximum value, right? This is number one. Next, you see, since we expect the isothermal core to be a small fraction of the total mass, this is one, again, approximation number one. Next approximation is number 2 is, we assume the isothermal core to be a small fraction of total mass of star. Okay, so this means that I can write m square minus mic square. This is of the order of m square. So if I do these two approximations, then you will see we will get P envelope is of the order of g by 4 pi into m square by r to the power 4. Now, okay, now you see at the boundary between the between the isothermal core and the envelope, the temperature of the gas in the envelope should be equal to the temperature of the isothermal core, right? So at the boundary, what we will have is the following: P is equal to Kb by mu mh rho T, right? So this thing will give me some temperature which will be the same as the temperature of the isothermal core, right? So this means PE envelope mh divided by rho envelope into Kb. Now let us approximate the density of the envelope at the boundary by the mean density. Let us approx density of envelope by mean density. There are so many approximations. You must be wondering. Of course, it's true. Indeed. And using this, we will get a general idea. That's also correct. Okay, so as a result, what we can have is just this relation. 4 by, sorry, this will be 4 by 4 pi r cube, and r is of the order of 1 by 3 gm by TIC mu envelope mh divided by kb. Okay, you must be wondering how we got this relation. Now basically, if this envelope expression is your relation C, and this previous envelope expression, pressure of envelope, was relation A, and this temperature TIC is your relation B, then the simultaneous application of all these three relations A, B and C, this will actually give you this result. Okay, and you have this relation. Okay, fine. So now we can turn this around and substitute this expression for R back into the relation A, which is the hydrostatic equilibrium expression. And this you will see, if we put it back in the hydrostatic equilibrium, this will give us P envelope is approximately 81 by 4 pi 1 by g cube m square kb t ic divided by mu envelope into mh, okay, whole to the power 4. Now this is the downward pressure of the envelope on the surface of the isothermal core, as we have shown you previously. Okay, fine. So we have calculated this pressure of envelope. Now what about this PIC? That is outward pressure from the isothermal core. So we will now calculate this. Now you see this outward pressure from the isothermal core, this is basically calculated using your virial theorem. Now let me write down the virial theorem in this form. So d of PV minus P by rho dm is equal to minus 1 by 3 gm dm by r. Now integrating outward, let me write, integrating outward from the center to surface of isothermal core, what we have is this relation 3 PIC VIC minus 3 0 to MIC into P by rho dm equal to, minus sign will be there, 0 to MIC GM dm by R. Okay, of course you understand that this IC refers to this isothermal core. Okay, basically when I write the small IC, I mean the small IC, this basically I mean to say that the values at the surface of isothermal core surface. Okay, now you see the first term here, this thing, what is this value? This is basically your 4 pi RIC whole cube into PIC. 4 by 3 term, and this 3 cancels out, so this. Now we will do an approximation. Let us assume the core to be an ideal gas. Then the second term will become MIC P by rho dm is equal to 2 UIC, where UIC is basically the internal energy of ideal gas. Okay, so that we can write UIC is equal to 3 by 2 into MIC divided by mu IC into MH into KB TIC. Okay, now what about this value, this one, the right side expression? Now on the right hand side we have the gravitational potential energy of the isothermal core. So we can write it as, so RHS term, let me write it. So 0 to MIC GM dm by R. This is basically equal to the gravitational potential of the isothermal core, and this is approximately minus 3 by 5 G M IC whole square divided by RIC. Okay, where this factor arises due to assumption of constant density of core. Okay, now if we combine all of these terms together, then we have, for the pressure, combining all terms, you see, we will have this expression: PIC is equal to 3 by 4 pi R IC whole cube MIC KB TIC into divided by mu IC into MH minus G MIC whole square whole divided by 5 of RIC. Okay, now you see the term in the brackets is quadratic in MIC. This is MIC to the power 1, this is power 2, and so this means that there is a maximum value. Okay, and this means, so there is a maximum value of MIC, and you can do this out extremum calculation, and you will see that this maximum value is at MIC is equal to 5 by 2 KB TIC RIC whole divided by G mu IC MH. Okay, this implies that the pressure of the isothermal core of mass MIC and temperature TIC has an upper bound. So this means pressure of isothermal core of mass MIC and temperature TIC has an upper bound, and so what is the upper bound? So this PIC max is given by, basically if you do the maths, you will see that the value comes out to be, although it's not very difficult, you see, it will be, you will be able to get this value to KB TIC divided by mu IC into MH mass of hydrogen whole to the power 4. Okay, fine. Now what we will do is that let us equate the maximum isothermal core pressure to the envelope pressure, and if we do that, so equating the maximum isothermal core pressure to the envelope pressure, it gives us critical value for the mass fraction of isothermal core, and the value is this: I Q critical is equal to MIC divided by M. Okay, and this is basically your 375 by 1296 by mu envelope divided by mu of isothermal core whole square, and its approximate value is 0.54 into mu envelope divided by mu isothermal whole square, and this is known as Chandrashekhar Schonberg limit. Okay, a more rigorous calculation will give more rigorous calculation. Actually, using the polytropic model, it gives us this constant value to be approximately let me write it, Q critical. Again, this gives us the value of 0.37 into again mu envelope divided by mu IC whole square. So basically, if the isothermal core mass exceeds this mass, so let me do the interpretation. If the isothermal core mass exceeds 0.37 into mu envelope divided by mu IC whole square into your total mass M, then the core can't support the envelope. Okay, and it begins to collapse. Okay, now let us do an example in this regard. So suppose a star starts out with a composition of x is equal to 0.7, y is equal to 0.26, and z is equal to 0.04. So basically solar distribution. So the metals have the solar distribution, right? Now if we assume that suppose all hydrogen is burnt in core, right? So the question is, what is the Chandrashekhar Schonberg limit for the star? Can you calculate this? Just try it out. Well, it is not very hard. Basically, you see, for the envelope, we have 1 by mu envelope is equal to 1 by mu I plus 1 by mu E, and this is just x plus y by 4 plus z by A average, right, plus half of 1 plus x. Okay, now solar metallicity has your A average of, you must remember this value, 15.5, and so this turns out, if you put in all the values, you will see that we get mu envelope is equal to 0.618. Okay, now for, let me write it on the other page. For isothermal core, right, we note that Z doesn't change. Therefore, Y is equal to 0.96 solar metallicity. You remember what I asked? Remember this, right? Now isothermal core, this means all hydrogen is burnt, Z doesn't change. So what about Y? Y is just the rest. So right now we will have, since x is equal to 0, y plus z is equal to 1. Since z doesn't change, so y is equal to 1 minus z equal to 0.96. Okay? Okay. So we can write 1 by mu IC is equal to half plus y by 4 plus z by A average, right? And you will see that this turns out to be 0.7426. So this gives us mu IC is equal to 1.346, and so we can calculate the Schonberg-Chandrasekhar limit using the exact expression mu envelope divided by mu IC whole square, and you will see that the value is 0.078.